everybody. This is our monthly Impossible Metals webinar, and I'm very pleased to be able to announce that Bob Galyen will be talking about the complex world of batteries and how Impossible Metals changes the landscape. Now, Bob really needs no introduction. He is known by almost everyone in the industry, having been, I believe, the #2 employee at CATL, and was CTO for many, many years and ultimately retired. CATL, I think everyone should know, is like the world's biggest battery manufacturer. 70% maybe Bob can correct me, of batteries by kilowatt hour are produced by them. Prior to CATL, Bob spent a long time at General Motors and now has an impressive list of awards and accolades that I won't read out, but Bob has been a great friend to Impossible Metals, incredibly well known in the industry, and we are very honored that he agreed to give this webinar. So thank you very much, Bob. Over to you.
Well, Oliver, thank you very much for that kind introduction. I basically took this slide deck that I've used in presentations at University of Michigan, University of Brisbane, even in Birmingham, England, at the last conference there, and used some of the slides as introductory materials for the battery show this year. So if some of the people that are on the call may see some slides that may look familiar to you, it probably is, because it's more about the story and that it's trying to tell the world as to what's going on and why we need to pay attention to Impossible Metals. So why don't we go ahead and get started with this? So many people wonder why was China so successful in batteries? We're going to cover that in a little more detail. Second, we'll cover is where are batteries financially? They're becoming a Goliath in the world of economy around the world. We'll talk about battery systems integration for a few minutes, then megatrends, and probably one of the most important for Impossible Metals is the law of supply and demand in the circular economy. We'll talk a few minutes about Leibridge Initiative and the Inflation Reduction Act. We'll talk about the government's response to the Inflation Reduction Act and what Leibridge did, as well as I always like to throw in my top 10 list that I stole from Dave Letterman, being the famous comedian, except mine's pretty serious. And we'll talk about in an emphasis on the nickel, manganese, cobalt technologies that give us higher energy densities. And then finally, we'll talk about technologies on the horizon that could be in competition and or in support of deep sea mining. So let's dive in. So many people have asked me this question: why was China so successful? Well, there's 4 key reasons I identified during my 7.5 years as a CTO there at CATL. Well, number 1 was government support. Environmental concerns and difficulty in starting up a new technical revolution is not easy. So culturally, the Chinese government basically incentivized battery manufacturers and car manufacturers to create electric vehicles. And they had another good incentive to do that through tax assistance. So government support in China was well-founded and initiated early in the game. Secondly, there was technology. Now, a lot of people think that China had a malicious intent of taking over the world with batteries. No, it was something that was basically handed to China over more than a couple of decades, making consumer electronic batteries. Because in order to make consumer electronic products like pads, phones, small electronic toys and things that use a lot of electricity, batteries was a natural. But in order to make those consumer electronics, you have to have materials. And in order to have materials, you got to have a means of converting what Mother Earth hands to you through mining or creation from ocean or brine. You need some kind of a manufacturing process to convert those raw materials from Mother Nature into something that can be used in making batteries. So China did. They developed that capability. And in many slide decks I've seen since I put this one together earlier this year, there's a lot of percentage-wise, 66 to 99% of all the materials in the world for making lithium-ion batteries come through China, for the mere fact that they created the infrastructure early. That's where North America and Europe both need to go. The third primary reason was private equity investment. There's a lot of investors in China that came from all walks of life: sugar, flour, electronics, steel, oil. Just lots of different people that have money in China that made a fortune off of different walks of life. And those basically moved to batteries because they were going to get higher margins, particularly with support from government agents across the board in China. So the private equity investment is a big part of it. And you'll see later that's the part of the reason that we're moving slower in North America and in Europe. Then fourth is the M&Ms. It's not those cute little chocolate things that the grandkids steal off my desk here at home, but it's the man in the machines. In order to run a process that is in the gigawatt level of production, you need to educate and train people in all aspects of operations. In order to run those machines, you'll also have to have the machines built that are capable of producing the gigawatt level productions in a parts per billion failure rate mode. That is not simple. So educating people, building machines capable, doesn't mean you're going to be successful. You have to have both, and it has to be done in the right way, or you'll have a miserable failure. I was quite fortunate that I had a great team at CATL, and we did a good job in that regard. But these are the four key reasons I identified during my time working in China why they were so successful in batteries. At the end of this presentation, I'm wide open for questions, so I'll move along here quickly so that we can get through all the material. Now, this slide was put together more than anything to kind of recalibrate my dear friends in Detroit that wanted to pound on their chest, claiming that they were, you know, the big dogs in the park. But they still are. They're very important customers. But also, we have to note that this list looks like it's got notable absence of a few line items. Well, those few line items are the battery manufacturers that I intentionally put in red. But as of June the 4th of this year, and I didn't have time to dust it off before this call today, I put in here the battery manufacturers in red to compare those to some of the other manufacturers that are on the list. And one notable difference that you'll find here, that most of the battery manufacturers, like Toyota in this case, were basically built on bricks, mortar, intellectual property, and people. It's just amazing to me that these battery manufacturers have become such large corporations from a market cap standpoint to compare to the automotive sector. I've also got some heavy duty in here, such as Cummins and even aerospace. The Boeing and Airbus is on this list just for comparison. So battery manufacturers have become major players in the global economics of the world. That's a bit of a Rubik's Cube because we see new technologies crawling out of the woodwork almost on a weekly basis. You can see we've got ships in there, we've got construction equipment in there. In fact, I drove that little backhoe. That's a 12-ton backhoe. I drove that the last week that I worked at CATL, and it drove its big brother, the 22-ton backhoe, and a 20-ton payloader, all electrified with batteries. We also see vertical takeoff and landing. We see fixed wing aircraft, and certainly automotive sector. Every week we hear about new announcements there, as well as energy storage that supports wind, solar, and now I see a movement into wave storage because people around the world are finding out that Mother Earth hands us a lot of energy in the form of tidal wave activity out in the ocean, and they're capitalizing on the tidal currents and the tidal wave generation capabilities. Now, I threw this slide in just for the fact that some of the people on the line may not be as battery geeks as we are in the battery industry, and understanding that there's basically three different formats that go into building cells today. There are others, but these are the three predominant cell architectures, such as a prismatic cell, a cylindrical cell, and a pouch cell. And I've intentionally included some pictures here indicating that all three of these cell structures can be integrated into structural concepts that many of the battery manufacturers are integrating into the vehicle manufacturers' systems, or vehicle manufacturers themselves are building structural packs in their vehicle chassis. Now, at the bottom of the slide, you'll see that I put in the predominant packaging scheme for the mobility sector and the 3 evolutionary steps that we've taken. In the early days of electrification, we saw module to pack configurations were the predominant driver. Today, we see a predominance of cell to pack designs. Some are calling them blade cells, or different versions of blade cells going into making cell to pack configurations. But the whole point here is that we're getting more integrated cell architectures into the battery packs. In the future, as we see other battery technologies coming to the front, we'll probably see cell to chassis architectures. They are in progress today, but have not been released to the public for sale at this time. So I put this in more than anything to let everybody know that there's a revolutionary process going on in the design and architecture of battery systems going into packs. Now, we all know that electrification is one of the biggest megatrends worldwide. Now, my slide is...
I'm not sure about that.
Google's talking to me in the background. I'm not sure why she's talking to me. That happens frequently. But the electrification is transforming industries all over the world. Now, this slide is a little outdated. I need to dust it off a bit, but it still holds true today, even though the numbers have changed. Improved battery economics. We all know that the cost is coming down and that the energy density is going up. So in terms of improved economics, we're seeing a twofer here. We see improved energy and reduction in cost. That's a good thing. We also see signs of increasing EV adoption because sales volumes are going up, where people are getting past range anxiety with the announcement of many of the car companies putting in charging infrastructure, much like Tesla did years ago. In fact, many of them have adopted the Tesla charging infrastructure and interface so that they can utilize the Tesla chargers. And we also see that infrastructure is improving quite a bit in terms of amount of stations that will be in place within the next 2 years. Third, we see an increased renewable energy usage. And this is one of the primary things that many of my clients ask me when we're helping them decide on site selection for where to build factories for both cells and for supply chain networks is, how much renewable energy do you have on your local grid? Because this is becoming an important point, whether it's solar or wind or both. Companies around the world, not only North America and Europe, but other places around the world, we're seeing major increases in renewable energy usage. And then the fourth area is smart grid demands. We're finding that batteries are finding a foothold, particularly in societies around the world where we have a lack of good infrastructure. In fact, many countries that have had architecture are getting old and dilapidated, and batteries actually fit into some of those architectures much better today than they did in yesteryear. So batteries will become a predominant player, I think, in smart grids in the future, both in front of the meter and behind the meter. Now, the old law of supply and demand that we learned in our economics classes in school will come back to haunt us. So here we go. The demand, now this was a study done last October, so it's a year old, I admit that. I need to dust this off too, but the demand for lithium-ion batteries that were put out by McKinsey and Company last October said that we had over 4 terawatts of battery demand between 2015 going into 2030. That's a huge increase. In fact, they state that this is about a 32% compounded annual growth rate. Now, when we match that up with the amount of cell production capacity that was estimated at that time, we saw that there's a shortfall of over a terawatt hour of production by the year 2030. That means that we just can't build battery plants fast enough, which also means we can't build enough conversion material production fast enough to keep up with the demand that we're expecting. Until recent times, we've seen a very rapid growth in electrification, but in recent months, we've seen small decline in growth rate, particularly in China. Now, when we look at the circular economy perspective, the material-centric perspective was put together in this particular slide deck, and I've got the reference over on the far right-hand side. There's a lot of elements to this centric perspective, much like what I had to deal with in doing lead-acid batteries for 24 years of my life. We have now battery technologies that can be taken out of its first primary application and put into a secondary application, so we can call that reuse. We can also call it refurbishment, where we take the same battery pack, refurbish it, and put it into another application. We can also do recycling, and we can take that recycling to its fundamental elements and compounds that were recovered from the batteries, then put them back into the primary use of building cells again. The only problem with the circular economy with the lithium battery versus a lead acid battery, where lead acid usually failed in roughly 3 to 6 years, now we're looking at battery systems that fail in roughly 10 to 15 years. So many of the precious materials that are going into building cars today won't come back in the circular economy for about 10 to 15 years, depending upon how often people decide they want to turn their cars in. Many of us that have cell phones understand that technology is changing so rapidly in these nice little handheld devices that we typically turn them in and recover the materials much faster in consumer electronic product. But for an asset like a car, a bus, or a truck, they typically are longer recycle times. Now, during my tenure as CTO at CATL, we did do the calculations on bus applications because it was predominantly a lithium iron phosphate technology. But those batteries were coming back in roughly 5 years because the duty cycle on a bus is so much more rigorous than on a personal mobility vehicle called a car. So it depends on the application. It depends on what the usage is and when those raw materials may get recovered and brought back through the system. But in the meantime, we've got to be able to fill the supply chain network with new materials. I mentioned earlier that I'd talk about the Lightbridge Initiative. I was fortunate to be chosen to be on committee number 1 of the Lightbridge Initiative. And out of that initiative, we had 24 action items that were given to the U.S. House and Senate for consideration for future legislation. But the 3 top challenges that we identified during that work that we did in the Lightbridge committees, and there was a lot of time spent on this, was number 1 was a lack of attractive returns on U.S. capacity investment. If you remember, this was one of my metrics that I graded China so highly on, is that the guys that had money in China had no problem investing in battery technology because their government was supporting it quite well. So they did get good returns by putting money into battery technology in China, and many of the people became millionaires or billionaires from that opportunity. Secondly, we had a challenge of lengthy and uncertain timelines to secure permits and project approval, especially upstream, meaning mining and also material processing. We just have a very difficult time getting things started in both Europe and in North America on this particular topic, because in most countries, it doesn't take as long to put a mine in operation as it does in the US or in Europe, because we do have more mature societies and we also expect better environmental protection. And this too slows down that whole process. Not that it's a bad thing, but it is a bad thing when you're trying to move quickly to compete with other societies around the world, particularly when it relates to national security issues like batteries have become. So this is a really important point, that moving faster is being slowed down by our own governments for project approvals because of permitting. Third is a lack of access to energy raw material supply. Today, many countries are shipping their products to China to get the raw ore processed and turned into materials that are then shipped back to them or to their countries so that they can build batteries from them. So many countries are moving aggressively now to create infrastructure for processing raw ore into something that can be used in making batteries. I think this is a really important point for everyone that's on the call today, because this is one of the key things that Impossible Metals will do, is help break down this barrier of the raw material supply chain, because it's using a totally different approach. And it also addresses the challenge in item number 2, because securing the permits are different depending upon where you are in your mining operation or underwater harvesting of nodules from the ocean bed floor. Those permits could come from countries that were within a 200-mile shoreline limit. Anything outside that goes through United Nations, and Oliver can speak to this later because he's more up to date on that than I am. But those approvals can go through the United Nations for being able to initiate harvesting of the nodules from the ocean bed floor. Now, what was the U.S. legislation response to the Lightbridge Initiative? Well, they kind of jumped the rope a little bit by going directly to an Inflation Reduction Act before everything was complete through Lightbridge Initiative. And what they announced was a clean energy manufacturing credit. And I'll draw your attention to the lower half of this chart, because the advanced manufacturing production credit is extremely important, because if you build any of those active materials that are listed under the requirements section, such as cathode or anode materials, the foils, electrochemically active materials, which is what Impossible Metals will provide, in solvents and additives and electrolyte salts, they're going to get a 10% of their cost returned to them by the U.S. government, because they're making active materials within the confines of the U.S. or their strategic partners that are considered friendlies, not foes. Secondly, if the manufacturer is building cells in the United States, they can get as much as a $35 per kilowatt hour return on the build of those cells in this country. Battery modules, you can get an additional $10 per kilowatt hour if those modules are manufactured with materials and products made here in North America, as well as critical materials, including aluminum, cobalt, graphite, lithium, manganese, nickel, and so on, will get a 10% cost return from the government. But you can only apply for 2 of the credits that are above. So what does that mean in terms of dollars to some companies? Well, I thought this chart coming next from this report done by Bloomberg was pretty phenomenal, because it shows that during the life of the IRA, which runs through year 2032, Tesla, GM, and Ford could potentially receive up to $41 billion in credits by the year end of 2032, which is pretty amazing, because Tesla gets that, the $41 billion in credit, which is far more than their key Detroit rivals. So when you look at this article, you can find out all the numbers in there, but it is remarkable how much money the U.S. government is committed to return to the manufacturers within the next decade. I've thrown in a couple of charts from this report that was put out by the Volta Foundation, because I was one of the authors of the report from Volta Foundation. So basically, this is a cut and paste from their report. And this particular slide was put together by Wood Mackenzie. It shows specifically the major nickel, manganese, cobalt producers and the 22 production capacities of each of these different companies. So clearly, Impossible Metals are going to be in there competing with some pretty big companies, or they may actually be suppliers to many of these companies, because the ore that they will derive from the nodules harvested from the ocean bed floor will be an important part of fulfilling the supply chain of the future, because all these capacities are going up each year, year over year. Now, I want to get into my top 10 list. And again, I stole this idea from David Letterman. He graduated 3 years ahead of me at Ball State University. But this top 10 list is an important list, and I probably will dust this off again before the end of this year, since I derived it early January of this year, but it is still held true throughout the entire first 10 months of this year, at least, that there is remarkable growth in batteries. It doesn't matter who is putting together the report. Remarkable growth is a milestone that you just can't get past. And it's because the adoption rate of electrification worldwide is growing remarkably fast. Now, this particular report showed a 34% compound annual growth rate. So the massive demand growth with over 300 billion, now that number has been refined to over 600 billion worldwide by the year 2030, if not 700 billion. There's just been a lot more money being thrown at electrification over the last several months. Now, government engagement is important, and I remember the first time I put this slide up at the NAATBatt conference this year, my friend from the DOE, Dave Howell, basically this was knowledge that their team put together doing a SWOT analysis. But many governments around the world are not as organized, if you will, as China and the United States. And there are many countries scrambling on what to do, what model to follow, and a lack of knowledge in making decisions. So this SWOT analysis is just simply a methodology of looking at what they need to do, when they need to do it, and how they need to do it. Third is technology decisions. What technology should be used? Should they use nickel, manganese, cobalt in their electrodes, or should they use LFP, LMFP, or others? And then which form factor to put it in is not easy. So the combination of chemistry and packaging becomes increasingly important in different vehicle architectures, because these different cell architectures and packaging drive the aerodynamic efficiency of the vehicles, depending upon how the engineers contrive the battery pack design, because it does have an impact on the hood line and the fender wells and the top hat of the vehicle, which changes the aerodynamic efficiency, which impacts range. So it's a bit of a do loop, if you will, or an endless do cycle in doing battery pack designs integrated within the vehicle architecture. Number 4 is the infrastructure required. We talked about this a little bit earlier, but there have been charging capacity efficiencies. There still are worldwide, but many countries around the world are remedying that very quickly by putting in more charging infrastructure. So we're hoping by the end of this decade that this will be not a problem anywhere in the world, but will be resolved and people will get past the concern of where do I plug in my electric vehicle. Number 5 on the list is industrialization. This was a serious problem during the COVID era. We were looking at time frames for structural steel being out 54 weeks, roofing materials over 2.5 years, and the lean up concrete were out there in the 12 to 18 month range. So trying to build a building during the COVID time frame was just almost impossible if you wanted to get it started quickly. Now today we see a different problem, and that is so many people are running to build new buildings, whether it's the cell manufacturer, module or pack manufacturers, along with the large supply chain network that are trying to build factories. Now we see the industrialization being built on a concern over so many factories being built, not on material availability because you can't ship anything because of COVID. So the reasons for industrialization being a pinch point have changed in the last 2 years. Number 6 is fire concerns. We all know that this is a big concern, particularly with higher energy density battery systems that typically use nickel, manganese, cobalt, but many companies have figured a way around this. Number 1 is good quality products help you keep from having fires in the first place, and you're not as worried about the propagation and prevention, but you still must do it. The HECL guys love me because I put their slide deck in this slide deck, but there's lots of other companies, 3M and Dow and other companies also make these type of propagation and prevention measures, along with a host of other private companies that also make materials that go into helping prevention and propagation. But I think this is an important point that we can't get around right now because there have been some fires and fire concerns, and most of them are related to quality. Number 7 is materials. I remember that the young lady from Bloomberg New Energy Finance was in the crowd when I first used her slide in a presentation, and these numbers have actually gone up in terms of the deficiencies in the cell level in the lithium, nickel, cobalt, manganese, and graphite. So opening new mines around the world is critical to minimize these deficiencies, and clearly impossible metals in their ability to harvest the nodules from the ocean bed floor is going to be really important. But it's not only just for these raw materials. Copper, in my opinion, will become one of those commodity-based materials today, will become more precious in the future because we're using copper in so many different parts of an electric vehicle application, whether it's motor windings, whether it's in the wiring harnesses, in the inverter, in other systems, and the battery itself. I think copper is going to be an important one, and many of the nodules that we're harvesting from the ocean bed floor does have a large amount of copper in it. We'll also see that the harvesting of some of these nodules will give us some critical materials for electric magnets, that is permanent magnets. So the praseodymium, the neodymium, and those other materials that go into making permanent magnets will become important, and some of those materials are in the nodules that are harvested. Now, this slide goes along with the one that was just before it, and it gives you a visual breakdown, and I have to hand it to the visualcapitalist.com website. They did a great job of being able to pictorially represent so the human mind can understand better what the amount of materials go into these battery packs. I think they just did an outstanding job on that. But what you'll notice in this slide also is the chart on the right showing the 3 different NMC technologies in the NCA compared to LFP and the amount of different materials that can be harvested from these nodules off the ocean bed floor that go into building these higher energy density battery pack systems. Now, we've seen a bit of a trend of companies going more toward the LFP recently because they didn't think they're going to have enough of the nickel, manganese, cobalt at a price point that makes them financially viable. But Impossible Metals is going to change that paradigm. I'm concerned that many people are running toward LFP when in fact an NMC solution could be as cost effective in the future as an LFP. Number 8 on the list is recycling. Recycling is a complex word. Recycling includes the collection, the shipping, the disassembly, the shredding, the reconstitution of those materials into their fundamental elements back to something that can be reused in battery. So you're looking at roughly 10 to 12 steps in a recycling scheme that we call recycling. So major effort is going into this. But again, recycling is tied to timing, and timing is that many of these materials that are going into early stage batteries, we won't see those come back for 10 to 15 years, depending upon how long people keep the batteries or how much those batteries go into a secondary use application. Number 9 on the list is corporate structuring. We're seeing a plethora of companies that are ganging up together to try to get a cost leverage or a volume leverage. And this chart, again, is dated. This is put together by Wood Mackenzie over a year ago, but it still holds true that many of the companies that are on this list, showing all the cell manufacturers, that joint ventures are important point for them as well as their car manufacturers, as well as their raw material suppliers, which is portrayed in the next slide. You'll see a lot of the larger material suppliers on the far left side, and many of the large car companies on the right side, and then the cell manufacturers in the middle. What you're seeing is financially and business-wise architectures of the car companies working with the cell manufacturers and working with the raw suppliers, or all three ganging up to create a better value chain. So we're seeing a change, a revolutionary change that wasn't quite possible in the internal combustion engine world, but now we're seeing different business models coming out of the electrification movement. And we're not seeing this just in China, we're seeing it in North America and in Europe and other regions around the world. We certainly saw a lot of discussion going on when I was in Dubai 2 weeks ago for a conference. Last but not least in the top 10 list is education and training. We certainly do need to train our workforce, including scientists, engineers, lawyers, academicians, college, high school, even grade school kids. Many of us were taught not to play with matches around gasoline when we were kids, because of concern of getting burned. We also need to teach our young children not to play with high voltage systems, particularly if they're around a car that their dad or brother or uncle may be working on at home that may be electrified, because high voltage systems can be dangerous if not treated properly. So there's a lot of education all the way up to and including our people that work in the manufacturing plants. I jokingly say that during my tenure as CTO at CATL that I worked as a guy all the way from the angstrom level to the meter level, working on atomic structures of making good active materials, product design, including cell design, module design, pack design, and all the way up through and including crash testing of the vehicle with the battery pack systems in it. So there's a lot of education training around the electrification movement because there's so much to learn and all new technologies that are being implemented in these vehicles. Now we're going to talk about some supporting technologies. The concept of vertical stacking is real. I've been practicing this since coming back from China, where we find companies that want to work together because one begets another material that goes into the next process flow. And this is working well because each vertical integration stack, if there's a cost savings with each one of them, could give North America and or Europe a leverage or a cost advantage over any competing countries that have a head start of us on technologies. So let's just talk about a couple of them here. One is a chromatographic separation technology that could potentially be used by Impossible Metals. We know that Impossible Metals is planning on using a biological degradation process using bacteria, but in the absence of that not working as well or not have a high enough throughput, this could be a backup plan where chromatographic separation is a reality. And this is being conducted by a company not more than a 7-minute drive from my home here in the state of Indiana. Now, this has been manifested in reality by both processing ore material, I've seen it, and I've also seen him do the black mass degradation and then separation. And you can see on the right-hand side a series of beakers that literally I was there the day that they did this study, and the lithium comes off because it's the lightest metal, then manganese, then cobalt, then nickel, as expected in chromatographic separation. Well, what is so amazing to me is that you can control the purity levels, either 3 nines or 4 nines purity or higher, depending upon the speed at which you're doing the chromatographic separation of these metals. So in essence, you create a highly pure material that can then be reconstituted in building the nickel, manganese, cobalt of your choice. Now, also, there's companies out there that have new technologies like 6K that can produce a material that is a much more cost-effective product from the raw materials that Impossible Mining could go harvest from the ocean bed floor and build better active materials through a different process using superheated plasma. In this case, they take a 2 to 3 day hydrological process or hydrology process and turn it into a 2 to 3 second process and add on a couple of hours for coating. Now you've got an active material that can go directly into batteries. So it's a huge processing cost reduction, a huge reduction in hazardous waste, and a reduction in water usage, and a better cost-effective product. Now, the government in the United States is starting to show support in deep sea mining support. This letter was written to President Biden by several members of Congress, and it's showing strong support of utilizing the minerals that are on the ocean bed floor in a responsible way, not an irresponsible way, so that these precious minerals can prevent a lot of the pollution that goes on from terrestrial-based mining processes. Now, we all hate to hear this, but it's true that Rio Tinto doesn't want to tell the whole world, but they have over 1% of the total production of pollutants that go into our atmosphere on an annual basis because of these large machines that are used in terrestrial mining. So this is, undersea mining is gaining support in governments around the world, but we have to get past the enigma of some of the sins that have been committed by other companies that are using less than responsible mining processes. Now, I threw in a couple of slides here to show differences in battery chemistries and their applications, and I just picked another slide out of the slide deck that the Volta Foundation put together for their annual report for 2023. And this shows some aerospace technology applications, and it shows some terrestrial-based applications and the different types of chemistries that go into them. So it's pretty clear that a large percentage of the materials that we will harvest from the ocean bed will go into some very important and critical products that require higher energy density technologies. Now, competing technologies. Nobody can do business without somebody giving them a competitive threat. Let's take a look at just a few of them. Now, I have to say this with either great pleasure or concern that CATL's sodium-ion battery is made with technologies that are cheaper and more cost-effective than NMC. However, the energy densities are so low that it won't stand or hold a candle to that of nickel, manganese, cobalt oxides if used in specific applications. So you will see sodium ion used in applications that do not require a lot of volumetric or gravimetric energy densities. And the one that really may be of concern as a future is condensed matter batteries, such as the one that Dr. Wu Kai announced last year at the Shanghai Auto Show. Now, there's a reason those cells are covered in gold paint, because the cost of these cells are extraordinarily high. But for applications like the aircraft that they're testing these batteries in China, clearly these are high-cost batteries, high energy density, but they won't compete on a volumetric or energy gravimetric basis with, sorry, I forgot to mute my phone. But the point here is that the condensed matter battery won't compete with the nickel, manganese, cobalt oxide batteries anytime in the near future, probably within the next decade and a half. Now, Lynova is another company that could be a competitive threat, but there are still metals that are in this battery that will be harvested from the ocean bed floor that can still be used. The only difference is they're using an organic redox active polymer in their cathode. The rest of the materials that go into this battery are required. That include lithium and includes the different salt materials and the copper and aluminum that go into the cell. Another technology that could be in competition, but more so on the power side, more so than on the energy density side, I think is one that's being developed in Australia called GMG, Graphene Manufacturing Group. They are making a unique graphene cathode material that gives extraordinarily high power densities, anywhere from 30 to 60 C rates, depending on the architecture of the cell. So with that, my closing comments are that Impossible Metals harvesting the polymetallic nodules off the ocean bed floor is one of the next logical steps in our evolutionary process in making electrified vehicles. During a Benchmark Minerals meeting in Washington, D.C. a few months ago, I got into an argument with some environmentalists at that conference over understanding what the difference was between responsible mining and irresponsible mining. And many of the people that are working as environmentalists don't have degrees in chemistry, nor degrees in biology, or degrees in engineering. I think part of the critical point is a lack of understanding in what is positive and what's negative with regard to harvesting minerals from the ocean bed floor. If it's done in a responsible way, it's far less intrusive on mankind, because my degrees are in chemistry and biology and spent 48 years in engineering. Their first generation robot is proven. I was there and got a chance to see it happen up in Canada. And I think Oliver will probably have better numbers on this than I am, but the first anticipated operations could be as early as 2025 and early 2026. And they're seeking strategic partnerships and getting into this business. But with that, Oliver, I'd like to close up and say thank you for the opportunity for this discussion, and I'll turn it back over to you and let you do the Q&A if you would like, because I'm here for answering questions from the audience.
Great. Well, thank you, Bob. That was wonderful. Really appreciate it. I'm actually going to hand over to Holly to actually manage the Q&A. And I think if people can, well, Holly, I'll leave it for you to manage how we want to do Q&A.
Sounds great. Thank you. So if you have a question for Bob, here we go. Go ahead and raise your hand, and I think I can get you connected here.
Yeah, and to raise your hand, there's a little hand icon in the bottom of your screen.
Perfect.
I saw a thumb go up for Tom Bruns there. I'm not sure. I can't see everybody on the screen because I don't have access to all of it.
All right. Gayatri, I'm sorry if I mispronounced that. You want to unmute yourself and ask Bob your question?
Yes, sure. Hello, Bob. How are you?
Great. Good to see you again.
Good to see you. I just had one question for you. For the recycling purpose, we have LFP chemistry and the NMC chemistry. The NMC chemistry has a more recycling materials in it, so the capital investment required for recycling would make sense, and that would also offset some of the pricing that might come for the NMC. But for the LFP, really people go after would be the lithium, and it is less. It is about 5% in the material. So, do you think that most of these LFP stacks or LFP modules or packs are going to end up in a landfill down the road, and people would have to reevaluate like which chemistry would make more sense for a circular economy?
Well, I think, Gayatri, that the recycling of the lithium out of the LFP is extremely important. And there's also some new technologies being developed where we may be able to recover some of the phosphates, and certainly we'll be able to recover some of the graphite coming out of the LFP battery technologies. Over the last year, I've seen remarkable changes in the strategy of how people put together their recycling architecture, if you will. And they're finding new and cost-effective ways of getting more of the precious materials out of LFP than they have in the past. Now, my feeling about this, Gayatri, is that we can build as many batteries in LFP and NMC as we want, and we still won't have enough. It's just a remarkable growth curve that we're seeing worldwide. But that's a good question, and I see that people are cost-effectively recycling LFP batteries.
Thank you.
Great, thank you. Okay, Chris.
Bob, thanks so much for the presentation. My name is Chris Dowd. I'm calling in from Collaborative Fund. We're an early stage venture fund. I'm interested in this area. So 2 quick questions. One is, at its logical conclusion, what is the level of production, extraction, volume of materials that could be brought out of the sea following this method? First question. And then the second one is really, you mentioned towards the end of the conversation the environmental concerns. I recognize there is a bit of a gap of understanding when it comes to the technology, but what do you think is an effective way to combat that and bring those groups on board with a recognition of the kind of macro constraints we're looking at on the path to electrification?
Both very good questions, Chris, and thank you. Let me answer your second question first, because education and training, getting people to understand that there are alternative technologies to retrieving or harvesting nodules from the ocean bed floor rather than dredging. Because everything that the car companies have talked about is dredging and how dreadful that is. And I say, well, you guys don't know what the new technologies are, because Impossible Metals are using a totally different approach. And they're saying, well, can that be cost effective? I said, if it's architected in the right way, yes, because it doesn't matter how you get the nodules. What we're most concerned about is minimizing the amount of disruption to the life forms that are at those depths, because many of those life forms we don't know about, but we can educate and train the artificial intelligence interface that Impossible Metals is devising. And we actually, during our first robot trial up in Canada, we had some very important marine biologists show up for the meeting so that we could ask them to help us in defining what sea life looks like down at that depth and how we program the artificial intelligence interface, as well as cut down on the amount of disturbance of the silt bed that's down there. The way that the dredging operation works is they basically take off a few centimeters of the ocean bed floor along with picking up the nodules, and anything in its path is going to get, it's kind of like a corn picker. It's picking corn in the middle of Indiana. You're going to destroy anything that's on those ears of corn or the stalks. And that's the same kind of process that is going on with the dredging. Plus the silt is then dumped back into the ocean, and it may take weeks, months, years for that silt to settle back down to the ocean bed floor. And in the meantime, it completely changes the behavior of the ocean around the area where that dredging is being done, because it blocks the sunlight from the phytoplankton, which is really important for helping control the levels of oxygen and CO2 in our atmosphere. Now, answering your first question, I think that the volumes that will be produced will start out smaller, probably in the tens of thousands of tons in first years of production, but grow rapidly as the technology is proven and that the business case works. And it will take some time to do that, because these kind of machines take some time to build, as well as deploy new ships that would go out and do more harvesting. So I think that's a great question, but Oliver probably would do a better job of answering that question than I, because he lives with it every day. I'm just an advisor. But good questions. So Oliver may want to come back to you maybe a little bit later with answering your questions directly with numbers that I probably can't quote. So Holly, next question.
Yeah. So we have a question in the chat from Beatrice Potenza. How far away are we from having solid state battery? I see lots of announcements, but is that really something real at this point?
That's a great question. And my standard answer is 7 to 10 years away. Because even if you have something that's benchtop ready, and many companies are announcing they've got solid state batteries that are ready, you've still got to run it through a validation process. That validation process can be as much as 4 to 7 years to get from basic benchtop variety of cells to a product that can be used in the vehicles. But some of those solid state batteries will also use the minerals that are going to be harvested by Impossible Metals from the ocean bed floor, because to make some of these batteries a reality, they include some of the metals that are being harvested. Good question, not a simple answer.
Thank you. Okay, Kieran?
Hi. Yeah, thank you, Holly. And Bob, thank you for a very informative presentation. Really, I found it educative. I have a question in a reference to the demand side. A couple of months ago, there was one paper released by IEA, and that addressed the issue of clean cooking related demands in Africa and other parts of the world. And that relates to approximately 2.7 billion people, maybe 600 million or so household using, say, in a hypothetical case, solar battery plus induction cooking. And I was wondering whether that particular part of the demand is included in any of the charts which you showed. Because when I look at it in that 3940 gigaton type of annual CO2 emission for the worldwide, this particular emission from cooking is not included. And I was wondering whether that particular area is of interest to battery community. Thank you.
Kieran, you're absolutely right. Almost all the charts that I have shown are very much transportation centric and not a lot about energy storage. They do have some energy storage in there, but new markets that are emerging, like the ones you just talked about, induction cooking for people that are in maybe less developed countries is critical, because it's helping them come out of poverty into a new lifestyle that is more acceptable, I'd say, or more convenient for them in terms of being able to do that. But because the battery is now an enabling factor, when you couple energy storage with solar panels or wind power, this gives you a better allocation, if you will, for energy that is used for refrigeration and for cooking in third world nations. Very good question. Again, not a good, easy answer, but there's markets like this emerging everywhere where you're seeing applications of drones and applications we've never seen before, cooking, lighting, anything that we can actually take things off the grid and power with stored energy out of batteries from renewable energy is being developed. So many of those applications are not included in the charts or the slides that I'm getting from many of the companies that you saw there. Thank you for asking.
Yeah, thank you, Bob.
Okay, Al Barnard? Oh, we can't hear you, Al. Let's see.
If we can't hear Al, maybe he can type it into the chat and we can answer him that way.
Great.
There, good idea.
Great minds think alike.
Holly, I don't have the chat box pulled up.
Oh, I'm sorry. I'll go ahead and read it.
Could you read it
Yeah,
to me, please?
Al says, I'm not well versed with the battery industry, but when I think of batteries, I think Duracell, and I didn't see that company listed in battery manufacturer. Sorry. Scientists emphasize the need for an energy transition, and engineers, y'all, confirm that we possess the necessary technology to achieve it. However, the prevailing global approach closely resembles the IPCC's business as usual model. How do you envision a successful energy transition unfolding? Thanks, Al.
That's a good question, Al. There's a lot of new technology being developed. Obviously, we can't cover all the different battery technologies. In fact, I'm helping write a book on education and training people on batteries in conjunction with SAE International. They'll probably be published within the next year and a half that will address these very topics. But there are lots of different electric chemistries out there. And the reason you don't see the batteries like a Duracell or other trade name companies that make the small cells are they're a dry chemistry. They're not, most of them are not rechargeable. Those that are terribly expensive, but most of those that are rechargeable are based on either a nickel or a lithium-based chemistry that can be recharged, and they do require expensive charge controllers on them. So that's why the cells are more expensive. But you're not going to see dry cells be a predominant player unless they're a dry coated type of technology. There are a lot of companies out there. Tesla bought Maxwell in the hopes of making dry electrode coating processes, but they still have a liquid state electrolyte in the battery. You may see a true solid state battery within the next decade that can achieve some of these metrics, but you don't see it today in any widespread production at this point. So hopefully that answered your question.
Great. All right. Girish?
Hi, Bob. Good to see you again after a long time.
Ganesh, it's always good to see you. I'll use the
Same
proper
here, sir.
pronunciation.
Oh, yeah, you're good. You're good. The question I had, I was intrigued by the sodium ion, sodium something battery that you mentioned that CATL is making for a car. It doesn't have very high energy density. Would that be a good choice for residential storage? Would that be an option?
It could be, Ganesh, if you got and the reason I can pronounce your name properly is my son-in-law's name is Ganesh.
Okay, nice.
So it's good to see you again, by the way. And,
yeah.
and I think the right answer to that is if the volumetric energy density and you got the space for it, that technology is a good choice for energy storage. The problem with those low gravimetric energy densities, they also have low volumetric energy densities. So if you got plenty of wide open space and fields to put it in, it's a good choice for supporting both solar and wind power. That's why I'm not terribly concerned about it in competing with nickel, manganese, cobalt, because I think what you're going to see is in the future a separation of these different chemistries going into different applications. And there won't be enough nickel, manganese, and cobalt in the industry to support just transportation alone, particularly when we start seeing some of these machines that are being developed for rail, marine, and cargo moving, fork trucks. You know, there's big fork truck companies now that are using nickel, manganese, cobalt oxide technologies in moving freight around. And you'll also see this in different kind of tugs and handling equipment at airport. So that's a good question.
Thank you, sir.
Great. Okay, well, we're at the 9:02 Pacific time. Bob, thank you so very much. This was an amazing presentation. Everybody, we will have this up on YouTube in the next, hopefully today, maybe Monday. So if you want to watch it again, have any more questions, we'd love to hear from you. And Bob, thank you. Thank you, thank you. And real quick, I'm just going to share, we have our next webinar scheduled for Friday, November 10th, deep sea mining from a Norwegian perspective, and we hope you can join us for that.